So far we saw Laplace transform, its properties and some examples. So let's see further properties of Laplace transform now. So especially we'll see how convolution in time domain affects the Laplace transform. So as we saw in the Fourier transform case, whenever we have two time domain signals, we convolve them in the time domain. What happens to their Laplace transform domain is simply the product of the two Laplace transform. This is very similar to what we saw in the Fourier transform case. But of course, we have to also understand what happens to the ROCs and poles and zeros. So let's first see why this is true. Okay. So what is convolution expression? So we have convolution of these two signals to be simply x of tau times y of t minus tau t tau. So this is the convolution. Now first what we'll do is we'll substitute the inverse Laplace transform equation for this. So we know that y of t according to the inverse Laplace transform is 1 by 2 pi j integral of sigma minus j infinity to sigma plus j infinity y of s e power st ds. So substituting that, what do we have here? Minus infinity to infinity x of tau y of t minus tau. So we have 2 pi j integral j infinity to plus j infinity y of s e power s. Instead of this t minus tau, we have ds d tau. Now we'll change the order of integration. When we change the order of integration, what do we get? Let's bring the constant outside and we'll do this integration y of s e power st. Then we'll have integral minus infinity to infinity x of tau e power minus s tau d tau. We'll integrate first this followed by ds. So this is nothing but the Laplace transform of x of s. So all we have now is 1 by 2 pi j integral of some z of s times e power st ds. And what is z of s? Z of s is equal to y of s times x of s. So if we apply Laplace transform on both sides, then we can see that the Laplace transform of x t convolved with y of t is equal to z of s, which is equal to y of s times x of s. So just like in the case of Fourier transform, when we have convolution in the time domain, it gets converted to multiplication in the Laplace domain. So what happens to the ROCs? The same thing that we analyzed earlier. So in this case, let's say there is an ROC for x of s, let's call that R1, and there is an ROC for y of s, let's call that R2. So x of s also should exist and y of s also should exist for this product to exist. So for that reason, the ROC of the product should be the intersection of the individual ROCs. So this is essential because otherwise the product will not exist simultaneously. So if you pick a value of s for which x of s exists but y of s does not exist, then the product cannot exist together. So the product can exist only for those values of s which belong to both R1 and R2. Now it can also so happen that y of s is the inverse of x of s. So in that case, when you take this product together, we just get a constant. So in that case, the ROC is the entire S-plane. So if it so happens that the convolution in the time domain results in a finite length signal, then the ROC can become the entire S-plane. So there are cases in which the ROC can become the entire S-plane, but the most usual case is the ROC is now reduced because it is an intersection of the individual ROCs. That's the most often encountered case. What happens to the poles and zeros? Now, if x and y, that is x of s and y of s, are rational, for x of s and y of s rational, what happens to the products? So let us say now x of s was of the form some product of s minus ai and s minus bi, and y of s was of the form, let us say, product of some s minus ci, s minus di. Now what is the product of these two? It is just the multiplication of these two, which means now the zeros will simply be ai's and ci's, and the poles will be bi's. Now the poles and zeros are included with one another. So the poles of x of s is also the poles of this product. The poles of y of s is also poles of this product. The zeros of x of s is also this zeros of this product, and zeros of y of s is also the zeros of this product. So there is an increase in the number of poles and zeros when you convolve. So what this tells us is when you convolve two signals, it can attain infinity at many more values than previously, and similarly it can attain zeros at many more values than previously. So if we have two signals in the time domain and we have the corresponding, let's say, Bode plot, if you want to find out what happens to the convolution, you can simply multiply these two in the Laplace domain. So the transfer function should also get multiplied. So the Bode plot now gets added up, because remember that the Bode plot is in the log domain. So in other words, when you plot it, the plot is 20 log mod of x of s is what we plot. Now when you have this product together, then you have y of s, which is now nothing but plus 20 log. So things become even easier in the Bode plot domain. So when you convolve two signals in the time domain and you want to understand what happens to their poles and zeros and how it affects the transfer function, all you have to do is, if you have the Bode plot of the individual signals, you just add the Bode plots and you're done. You don't have to worry much about what happens to the Bode plot for this convolution and all. So life becomes much simpler using these properties. So is there an equivalent for convolution in the S domain? So we had an equivalent to the convolution in the Fourier domain, right? We always had a duality. Something that is happening in the time domain will also reflect something in the frequency domain. So is there something similar to that here? We already saw that there is no duality here. So the first thing to note is, when we are convolving two signals in the S domain, the convolution is not as straightforward as it used to be earlier. Why is that? Because the convolution now is integral of x of some v times y of s minus v times dv. Now if you note this properly, here s is a complex number and so is v. So v is also another complex number. So this integration is not a plain one-dimensional integration that we had seen earlier. So this integration is now over a complex domain. So this integration is not over a single line. So if you remember, the inverse Laplace transform is over a single line. It's still over one dimension, and the Laplace transform, forward Laplace transform, is also over a single line from minus infinity to plus infinity, whereas this convolution is not anymore in just one dimension, but it is over a two-dimensional space. It's over the complex plane. So this is not equivalent to this one-dimensional convolution that we were used to. So for this reason, this does not result in the product in the time domain when you compute the inverse Laplace transform. So whenever you encounter a product of two signals in the time domain, you cannot convolve them in the Laplace domain and say that that is the corresponding Laplace transformation, simply because the convolution, the Laplace transformation itself, is a two-dimensional integral. Basically, you'll have to integrate it over a contour in the two dimensions. This is not equivalent to computing the product in the time domain and taking the Laplace transform, because that is a one-dimensional operation, whereas in the S domain we are doing a two-dimensional convolution operation. So there is no relationship when we have a product in time domain or when there is a convolution in the S domain. They are not related. So this is a disadvantage in Laplace transform. This was a big advantage in Fourier transform. So from this, we understood a lot of things. For example, like the sampling theorem and all came because of this relationship that existed when you multiply two signals in the time domain. So there is a drawback in the Laplace transform. We came to Laplace transform because it helped us to tackle some drawback in the Fourier transform, especially in the case where the Fourier transform did not exist. But it is not completely useful in all scenarios, because in scenarios where you want to analyze what happens to signals that you multiply together, there you cannot use Laplace transform anymore. There you have to go back to Fourier transform and then analyze what happens in the Fourier transform. So this is why we need both Laplace transform and Fourier transform. We cannot get rid of one and use the other. So there are certain cases where Fourier transform is the only transform that is useful for us. This is one example. And there are certain cases where Laplace transform is the only scenario where it is useful for us. That's the case where most signals Fourier transform do not exist, but the Laplace transform could exist.